The implicit differentiation is really just an instance of the chain rule. We'll start just by talking about what are explicit functions, and that will help us figure out what an implicit function is. So most of the functions we've been working with, all of them, most of the functions we've been working with in this chapter are explicit functions. They're the ones we're used to, where we have y is just given as a function of x. Like, there's an explicit function. It's set up so that if I know what x is, that one side is just x's, and it's set up so that once I figure it out, it just spits out what y is. Y equals, and then only things with x's. That's an explicit function. An equation that defines a relation between x and y that is not necessarily explicit, doesn't define y as a function of x. We call that an implicit function. We still use the word function, even though some of these equations may not define y as a function of x. Like, for example, we saw a lot of these in the first chapter. Like if you think about the equation for an ellipse. Y is not a function of x, because what makes something a function is that for every x there can be only one y. And with an ellipse, you sketch it like there's two y's for every x, right? Unless you're right on one of the very ends. So we call these equations an implicit function. They still define a relation between the two variables. So here's some examples. And they're just ones where they're an equation where it's just not set up as y equals and then stuff with x on the other side. So in this first one, this 3x plus 2y equals 6, that's implicit because it's not solved for y. As it turns out, that equation does define y as a function of x, and we can get an explicit form. It's a line, right? Here's an equation. Here's an implicit function, y squared plus x equals 3. It defines two different explicit functions, kind of puts them together. Y is not a function of x here, because if I were to solve for y, I get two possible x values. But it still implicitly defines a relationship between x and y. Here's an implicit function in part C, and I don't think you can get an explicit form. I think that x and y are kind of inextricable from each other here. And this one doesn't define any real valued relation at all. If you tried to, if you put maybe you subtract 4 on the other side, you get x squared plus y squared equals negative 4, and that's obviously impossible if we restrict ourselves to real numbers. So what we're going to do is work on, if we have equations like this, maybe we don't have y defined explicitly as a function of x, but we might still be interested in what dy dx is. For example, if I have an ellipse, maybe y isn't explicitly a function of x, but if I think of a point on that curve, I might still wonder what is the slope of the tangent line, and that should be well defined, right, for any particular xy coordinate. So differentiating, find dy dx. Finding dy dx for an implicit function is all about knowing what variable we're respecting. So I really hammer this notation in sections like this, dy dx, because I'm very explicitly saying I want to respect x here, and that's important to keep in mind as we're differentiating a function. So here's the way it works. And we'll go through an example here. First of all, this is an ellipse. How can we tell?
Both variables are squared.
And?
Different coefficients.
Different coefficients that are the same sign, right? So they're both positive. So we know that's an ellipse. It's also what? Centered at the origin, because there's no plain old x term or no y term. Now, if I'm going to find dy dx, the good news is we still get to use our regular old rules. But when I go to take the derivative of y squared, that's stuff to a power now. What I'm doing is I'm saying, I don't know what y is explicitly as a function of x, but it is some function of x. I know that I want to think of it that way because I want to respect x here. So when we start this process, what we're going to do now is, starting with this equation, you know how when we're working with an equation, back in algebra, learning algebra, we're like, oh, I could add 7 to both sides, or I could multiply both sides by 2, and we do more algebra and we realize, oh, I could take the ln of both sides, or I could take the square root of both sides. You can also differentiate both sides of an equation with respect to the same variable. So that's what we're going to do here. We're going to differentiate both sides with respect to x. And that first term, I'm going to apply, I've got stuff squared. So the power rule says I'm going to bring the power down. I'm going to have that stuff to the 1 less power, so just y to the first. But the chain rule says if I'm viewing y isn't just a variable, it is a function of x. That's stuff to a power. So I got to follow up by multiplying by the derivative of that stuff, which is dy dx. This is the chain rule as it appears in an implicit differentiation setting. If I move on to the next term, which is 2x squared, what's that derivative? 4x. Now, if I thought about applying the chain rule here, we'd say, oh, now multiply by the derivative of x. And that would be dx dx. And what do you think dx over dx is? 1. So usually we leave that out, right? Often when we're doing this, we don't write anything for that because, whoops, it's just equal to 1. And then on the other side, don't forget to take the derivative on the other side. What's the derivative of 5? 0. So I'm going to just rewrite this a little bit to clean it up. 2y dy dx plus 4x equals 0. Now, my goal was to find dy dx. This is progress because now I have an equation that has dy dx in it. I'm going to use algebra to solve for it. I'm going to think of dy dx as its own little function. So, or own equation that I'm going to solve. And it's really like a linear equation in dy dx. So I'm going to subtract 4x from both sides. And then what am I going to do next?
Divide by 2y.
Yeah, divide by 2y. And that gets us dy dx equals, if we reduce, minus 2x over y. Note that our expression for dy dx has both x's and y's, and that happens a lot of the time when we're doing an implicit differentiation. We didn't have y explicitly as a function of x up here, so it's probably, we can't really expect to always be able to get y as a function of only x there. Most of the time, it's going to involve both x's and y's. And it should, yeah, go ahead.
So the only time it wouldn't is in that first example where x and y aren't squared. That's when you could, the only spot you could define.
Well, here we could get an explicit version of, like this one you're talking about?
Yeah.
Yeah, like, because we could get that written as an explicit version. So if you use our implicit on this one, right? Like if I take the derivative all the way through this equation, you get what? 3 plus 2 dy dx equals 0. In use algebra, you'll get dy dx equals negative 3 halves, right? Constant, in fact, because, which comes as no surprise. Why am I not surprised that I got a constant there for dy dx? It's a line, right? It's a line with a constant slope. So, yeah. Also, it makes sense, I think, that we should have to have both x and y in this expression. If we, I won't go through the whole process of finding the foci and everything, but this is I think, a vertically oriented ellipse, so centered at the origin, something like that. So if I want the tangent line, I actually need to know both coordinates. If I knew just what x is, like let's say I wanted the tangent slope at this value of x. Well, the tangent slope up here is different than the tangent slope down here. I actually need to know both coordinates in order to figure out what the slope is tangent to a line. How's that? All right. Let's do another one. So we want to find dy dx. We're going to do the same thing. We're going to differentiate both sides with respect to x. So and if it's okay, I'm just going to throw this on the other side, equals 6. There's something we have to be a little bit careful about here. What's happening there?
Just the y squared.
Well, just the y squared, that's true. What else do we notice?
X doesn't have a power.
Yeah, or it's 1, but yeah.
Is there an issue with x being multiplied by y?
There's an issue with x being multiplied by y. And really all we need to realize is that x is being multiplied by y. This is a product. And we need to use the product rule to differentiate that term. So, yeah. So let's do that. Let's do a little side work on that. So our f function could be x. What's f prime? 1. Our g function is y squared. What is g prime? What is it?
2y.
Okay. I agree so far.
Oh, plus the derivative of
Yeah, times the derivative, times dy dx. Basically, if I'm respecting x, then, you know, if I'm just differentiating an x term, all my rules are normal. But if I'm differentiating anything that isn't x, I have to follow up by times the derivative of this variable with respect to x. If I were differentiating z cubed with respect to x, I'd get 3z squared times dz dx. Right, you have to multiply by the derivative of that variable with respect to, in this case, x. So we have those pieces. Let's go back to the equation. Let's start taking the derivative. What do we get if we take the derivative of 3y to the 4th?
12y to the third.
12y to the 3rd. Is that it? Times dy dx, yeah. So there's the derivative for that term. Now we've moved on to the product. So we're going to use the product rule, g f prime plus f g prime. So g times f prime is y squared times 1 plus f times g prime is x times 2y dy dx. Oops. So I'm going to just sort of draw a little box here. This part here is the derivative of that xy squared. And then we can move on to our last term, which is 2x cubed. What's that derivative?
6x squared dx over dx.
Yeah, or just times 1, right? Dx over dx is 1. You'll notice that we kind of left that out here. And the derivative of 6? 0. One of the common mistakes, and it's really just like an oversight or like a careless mistake, is people will work really hard to get the derivative on this side and then they'll just bring down the 6. They won't be thinking about differentiating the other side as well. So just, try to be careful about that. All right, I'm going to clean this up a little bit and then we can think about how we proceed. Our goal, it's keeping our eye on the ball. Our goal is to solve for dy dx. So what can I do?
Why did you get rid of the other dy dx at the end of that?
That's a dx dx.
Oh.
Yeah.
could subtract x squared
Mm-hmm.
and y squared. Get
Subtract. So subtract. Can you say it again? What are we subtracting?
y squared and 6x squared.
Yeah.
And then dividing by multiple.
Yeah. So when we do that, we have a couple of terms left. So we might not be ready to divide just yet, but we're pretty close. So,
So the goal is to get dy and dx by itself, so can you just subtract, or divide by, no.
so it's simpler than you think.
Can you factor out
Yeah.
2y?
We're going to just factor out, we could factor out a 2y, but I think so we'll do that, but we're also going to factor something else out. dy dx, yeah. And so while we're at it, we could factor out the 2y, but the most important thing here, what allows us to solve for dy dx is factoring out the dy dx. And this is the basic idea behind it. So let's see, let me do the 2y. That's 6y squared plus x. This technique is going to be pretty consistent throughout all of these implicit differentiation problems. There might be several terms, a couple, 3 terms that have a dy dx, but once we're just going to throw all the other terms. It's like it doesn't look linear at all, but our techniques of solving linear equations work, right? I'm gonna throw everything that doesn't have a dy dx over on the other side. Then I'm going to factor out the dy dx, and then I'm ready to divide. It's sort of like saying I'm combining the like terms, the like dy dx terms, and like this is their kind of algebraic coefficient. So now we divide. I'm going to divide by 2y times 6y squared plus x.
So why not expand the bottom? Well, with that. No, just make it.
What?
What stops us from going further with that?
I don't know if we could go further. I mean, nothing will cancel. Multiplying out the denominator, like multiplying out a product usually doesn't help unless that product is just one term in like a sum or difference of things. So, if we think about analysis of this curve, I could tell you that when y is 0, the derivative is undefined. That's easier to tell in this form than it would be if it were multiplied out. In fact, if I just go back to the other one, like how that presents itself in an actual curve, the derivative is also undefined here when y is 0. And when y is 0, that's when it's on the x-axis. That corresponds to this vertical line, right? A vertical line has no slope, right? That's an undefined slope because when you divide, the change in x is 0 that you would divide by. So the derivative is not defined. What that means is if we were looking at a graph of this curve, which no idea what it looks like. I could throw it into like Wolfram Alpha or something and see what it comes up with for a graph. But I would expect to maybe at y equals 0 see like maybe a vertical tangent lines there. In the implicit differentiation problems, it's not uncommon for things to get kind of ugly algebraically. So just, embrace it and try to have fun with it. You want to do another one?
Not really.
Okay, let's do another one. What do you notice when you look at this?
It's gross.
Okay, fair. What's going to be involved?
Product rule.
Yeah, where?
2x cubed y.
Yeah, so here's a product rule. Anything else you notice?
There's going to be a product rule with y squared plus x cubed.
I don't know that there's a product rule because I don't know how we want to view that product. Because y squared plus x is not a product. You're saying because we're cubing that stuff?
Yeah.
So I would say, I mean, we could think of it as a product, like that times that times that, like a triple product rule, so to speak. And there's an easier way.
Chain rule.
Yeah, like the regular old chain, like parentheses to a power. So here's where we're going to use that parentheses to a power and then say, okay, now I'll multiply by the derivative of that stuff inside. So maybe let's get to work. And the right side of the equation is kind of boring because it's, easy, right? So let's work on this product. What's our f function?
2x cubed.
Yep. So if f is 2x cubed, what is f prime?
6x squared.
6x squared times what? Nope. Times dx dx, or times 1.
It's okay if we don't write.
It's totally okay if you don't write out the dx dx. It's just equal to 1, and most of the time, if you see people writing out solutions to this, they'll probably leave that out. So that's really up to you. The g function, what's that? Y. And if g is equal to y, what's g prime? dy or dx, yeah. Yeah, 1 dy dx, or just dy dx. We're just basically saying, like, what's the derivative of y with respect to x? Oh, that's dy dx. That's what we're after. All right, so maybe let's begin. Let's start putting this together. G times f prime. G times f prime is y times 6x squared. I'm going to leave off the dx dx. Plus f times g prime is 2x cubed times dy dx. So I think that's the whole product. Does that look right to everybody? Okay. So now we can move on to the next term. It's that parentheses to a power. How do we start that? Like, how do we begin?
Find the derivative of the inside, right?
You could.
Drop the power in front of the parentheses.
We could drop the power in front of the... You're saying use the power rule, like the general power rule. And then when we do that, we'll have to find the derivative of the stuff inside. Yeah, so if we apply the power rule, what goes in the parentheses here? Yeah. Like, you don't change what's in the parentheses, right? It's the same stuff, just to the one less power. Then the chain rule says we're going to multiply by the derivative of what's inside. So notice that there's two terms to what's inside. Like that y squared plus x. So when I apply the chain rule, that'll have two terms in that derivative. I got to make sure I put that in parentheses. I have to multiply by the whole derivative of what's inside. What goes in those parentheses? Close. Yeah. I'm respecting x. Anytime I encounter a variable that is not x, and when I'm taking the derivative, I have to follow it by multiplying by its derivative with respect to x. And then here on the other side of the equation, what do we get? 4x cubed. We have differentiated this equation with respect to x. That's the first step. We have to be careful when we do it, but it is a somewhat mechanical operation. apply product or quotient rules as needed. Don't forget the chain rule, the implicit form of the chain rule. Like, just be really vigilant. Be paying attention, like, what variable am I respecting, and what variable is this that I'm differentiating right now? So, there's still a bunch of space left to do what? Algebra. Like, the calculus part is kind of over here, right? We differentiated. The rest of this problem is algebra. So we still need to get dy dx by itself. What do you notice about this equation that might make it a little bit more challenging? Where does dy dx live in this equation?
Inside the parentheses.
Yeah, I mean, we have one over here, like we've seen before, but the fact that we have it stuck inside a set of parentheses here means we have to fix that first. And we have a pretty simple way to fix that. That you all know what it is. You might not see it right now, but like, what if I had? I'm gonna put up.
Divide both sides because it's multiplication.
Well, look, we can divide both sides, but it won't be helpful
Oh, okay.
because then I'm gonna have I have to divide the whole side, so that I have to do that over here too.
Yeah.
Subtract y times 6x squared and basically just get the 6 squared plus x squared. Get the stuff in the red box away from the other stuff.
Well, yeah, we could, but that still won't allow us to. We'll still encounter the same problem if we divide by stuff. So I'm going to show you another equation that, believe it or not, is very relevant to what we're trying to do here. I'm going to tell me how to get the x out of the box.
You just draw it outside.
How do I get x out of the box there? Distribute. I can distribute it too. That's 6x plus 14. Bam. Done. Okay. Now, let's come back here. That's how I'm going to get the dy dx out, is I'm going to distribute the factor that's sitting outside. The factor maybe just looks a little uglier, but whatever. Who cares? But it's simple to do. I'm still just taking whatever's in that box. I'm just going to zap it. I'm going to multiply here, multiply there. And multiplying something by 1 is pretty easy. And multiplying two things together, it's not going to be so bad, I don't think. So let's do that. We have, 6x squared y plus 2x cubed dy dx. Now, if I distribute that stuff in the box to 2y dy dx, I'll have 6y squared plus x squared times dy dx. I'm going to pause there for a moment before I distribute it to the other term and just see, do you believe that or agree that this is the result when I multiply these things together? Is everything accounted for? What?
I was just wondering where you put the dy dx.
Oh, yeah. I just left it at the... There's nothing that says dy dx has to go at the end. I just like putting it there. All right, now when we distribute it to the 1, that's what we get. And then this is all equal to 4x cubed. So this stuff here is the result of what's up here. We just distributed that factor. And now we're in a position to say, okay, let's keep all of our, get all the dy dx's on one side. They all are already on the left side. So maybe anything that's not a dy dx term, throw it over on the other side. So we could subtract 6x squared y and subtract 3 paren y squared plus x quantity squared. So we have 2x cubed dy dx plus 6y, y squared plus x squared, dy dx equals 4x cubed minus 6x squared y minus 3 y squared plus x all squared. All the terms on the left side have a dy dx.
So you factor out the dy.
So we could factor out the dy dx, yeah. And now it's all over but the shouting. What's the last step?
Divide by that.
Divide by that. Well said. This is really about as far as I would go. It is not necessarily any simpler to, square this out and like expand everything. I don't think you'll end up with any like terms, like maybe one or two, but like it'll look almost uglier if you do that. So, so I would leave it like that. You could factor out 2 out of the bottom. You definitely will. You definitely could do that, but there's not a common factor of 2 up top, so it just wouldn't reduce. But it's totally like if somebody said I really want to factor that 2 out, I'd be like, do it. If somebody said I want to multiply everything out, I'd be like, fine if you must. But if somebody said I really want to factor that 2 out, I'd be like, all right, go for it.
The one that we did 1 or 2 ago.
Yeah.
One ago. If we didn't factor out that 2y.
That's fine.
Okay.
I mean, there might be some advantages analysis-wise because, we talked about how we could detect maybe a vertical tangent line at when y is equal to 0, right? Like knowing where the derivative is 0 and also knowing where the derivative is undefined can be helpful. But if you if you distributed that 2y through, fine.
I just wouldn't take it.
Or if you didn't take it out in the first place, fine.
That's okay.
Yeah. I mean, the only caveat is that if there's like a common factor that you're able to cancel, we should reduce, we should simplify that way. But a lot of the time with these implicit problems, it's not common that we end up with a situation that simplifies very nicely. We get situations like this and like that. Okay. Let's do another one. So this is, here's a curve defined by that function, by that equation. It's an implicit function. It does not define y as a function of x, and I can tell that because, here we go, fails the vertical line test like a whole bunch of times, right? But the derivative dy dx is well defined. If I know both coordinates, right? Like if I kind of trace along, like it seems like finding the slope of a tangent line is doable at any point. And that's what we're going to do. In fact, we're going to find dy dx and then we're going to use it to find the slope at the point 2, 4. So let's begin. We have our equation, x cubed plus y cubed minus 9xy equals 0. Let's begin taking the derivative. What do we get first?
3x squared times 1.
Mm-hmm.
dy dx.
No dy dx here. Can somebody tell me why? Because it's x. Yeah.
3y squared dy dx,
Yeah, why dy dx this time?
because we have a y.
Yeah. Yep. Now what about this last term? Product rule. Now be careful with that sign. You know, we were subtracting 9xy, right? So you could look at it a couple of different ways. If you want your f function to absorb the negative, so it's like f is negative 9x, that's fine, and y would just be, or g would just be y. Or if you do that, then you have to think of it as adding the negative xy. If you want to think of this as a subtraction, which is what I'm going to do right now, I'm going to bring it down, and then I'm going to think of the product just as this part here. All right, so when we do, let's see, g f prime plus f g prime. G times f prime. See, we didn't set up the side work yet, but let's see if we can't figure this out piecewise right on the spot. G times f prime, what should that look like?
Y times 9.
Mm-hmm. Plus f times g prime.
9x times 1.
9x times
dy dx.
dy dx, yeah. And this is all equal to 0 because the derivative of 0 is 0. Now I'm going to clean things up a little, distribute that negative. So now I have an equation with dy dx in it. That's awesome. Dy dx is what I want to find, and so if I have an equation with it, then we can use algebra to solve. What would you do first? And 9y, yeah. Yeah, subtracting, yeah, add 9y. Mm-hmm.
And then we divide by the what's left.
Yep. I think that's a good idea because,
Divide again by the 3.
yeah, well, so let's factor out the 3 dy dx on the left side, and while we're at it, why don't we also factor out a 3 on the right side? Right? And then when we divide, I think we'll be able to do some reducing. So that'd be y squared minus 3x. On the other side, if I factor out a 3, negative x squared plus 3y. And then we can divide by both of these. So those 3's are gone. So dy dx is, let's see, I think I'll switch around. I'll call that 3y minus x squared, just because I like leading with a positive coefficient, over y squared minus 3x. So there's dy dx. I mean, that's not the final answer they want us to get to, but it's necessary, because what they did want us to find was the slope of the tangent line at the point they gave us.
So you can just plug in x and y.
Yeah, so I noticed that we do need both coordinates. There were some problems like earlier on when we were first looking at tangent slopes and derivatives, where they'd be like, find the slope at this point, and they'd give you both coordinates, and sometimes it's confusing. They're like, oh, why did they give me this other coordinate when you don't need it? Because really, we only needed the x coordinate to find dy dx before. Now we actually legit need both coordinates to get that slope. That's at the point 2, 4. So we're going to plug in 2 for x and 4 for y. So 8/10 or 4/5. That's our derivative evaluated there, or you could call it m tan at the point 2, 4. How's that?
It was a lot smoother than the last one.
Yeah. There was just, a little bit less algebra to do, right? Yeah, okay. You're like, that's what I said. Yeah. Other questions or comments before we spend a little time talking about higher derivatives?
So we just always have to keep in mind what's in respect. So
Yeah.
you could do it the opposite way.
You could find dx dy.
Yeah. Okay.
Yep. That we don't have a nice interpretation for that. Like, it's not really a slope, right? Because it's. But technically, yeah, you could. I mean, this will come in. This will be super relevant when we look at applications, because you know how a derivative is a rate of change, and if I want to know how fast something's happening, like a time rate of change, maybe I've modeled it with some sort of equation. If you want a time rate of change, if you want to end up with something in liters per second or kilometers per hour, that means you're going to be differentiating with respect to time. And like, regardless of what your equation looks like, if that's the type of rate of change you're looking for, you're going to be respecting time. So like in the application problems, like that's always kind of very much like in the forefront, or should be in the forefront of our minds, like what we're thinking about when we model a problem and then use a derivative to solve it.
When we're modeling time, do you ever get a function that looks like the one that we have here? The like.
Oh, sure. Yeah. I mean, sorry, that was an excited response.
No, it's
but I can describe how it would look. And they won't be, well, actually, yeah, we'll see it a little bit when we look at curvilinear motion. But imagine that this is a track, right? A physical track that a ball bearing can roll around on. And we know it's rectangular equation. If I write an equation of a curve with x's and y's, we call that the rectangular equation. Imagine that I've just let the ball roll. So that, like, it's not just that this is its path, but it's its path over time. And I might be, maybe I know how fast it's moving in the x direction, but I want to be able to figure out, well, then how fast does it move in the y direction over time? Like, we're going to look at that a little bit when we do applications, when we look at curvilinear motion. So we're going to be finding a way to find, what is dx dt and dy dt, and you know what happens then? Then we have like, oh, I know how fast it's going in the x direction. I know how fast it's going in the y direction. That means I actually have components of a vector, of a velocity vector, and I can find its actual velocity vector as at a particular point in its path.
That sounds like hell and sounds pretty okay at the same time.
All right, I'll take it. Pretty okay.